yesterday. So we actually have only two questions left, question 7 and 8. Both questions 7 and 8 are on multi-level modulation. Let's start with question 7, which says that we have a microwave channel at a carrier frequency of 1.2 gig and a bandwidth of 12 megahertz. So it means that in the frequency domain, if we were to draw the spectra, it's centered at 1.2 gig and it has essentially a bandwidth, let's just draw it rectangular as an ideal bandwidth of 12 megahertz. So this here is 12 megahertz. And obviously, the left-hand side or the negative frequency components would be exactly the same as what we actually have there, obviously centered at minus 1.2 gig. So this here is 1.2 gigahertz. So the problem is that we need to transmit data over this channel at a data rate of 15 megabits per second using phase shift keying, some form of phase shift keying. So the question is determine an appropriate signaling system and then give the signal constellation. Now, if we have a data rate of 15 megabits per second, if we were to use binary PSK, we would know that binary PSK requires a bandwidth which is twice the data rate. So we would need a bandwidth of 30 megahertz, but we don't have that. We've only got 12 megahertz of bandwidth. So the only way in which we can fit a data rate of 15 megabits per second through a bandwidth that is less than 30 megahertz is by using multi-level signaling. Because we know that if we use multi-level signaling, then the required bandwidth is reduced by a factor of log to the base 2 of m, where m is the number of waveforms or the size of your modulation. In fact, we did say that the bandwidth, the general expression for the bandwidth is that the bandwidth is essentially approximately equal to 2 upon Ts. It just so happens in the binary case that Ts is equal to Tb, hence in that case the bandwidth would be 2 times Rb, where Rb is the data rate. But strictly speaking, for a general Ts, we can say that the bandwidth is 2 upon Ts. But for multi-level signaling, where we are transmitting multiple bits per symbol, then the symbol duration Ts would be the bit duration multiplied by the number of bits per symbol. And the number of bits per symbol is log to the base 2 of m. If capital M is equal to 2, then we are transmitting 1 bit per symbol, which is the binary case. If M is equal to 4, we are transmitting 4 bits per symbol, which is the case of QPSK, etc., etc. If M is 32, then we are transmitting 5 bits per symbol, etc., etc. So with this relationship between Ts and Tb, we can then say that the bandwidth as a general form is given by 2 divided by Tb times log to the base 2 of m, which is 2 times Rb being equal to 1 upon Tb divided by log to the base 2 of m. which means then actually we can say that the relationship between M, RB, and the bandwidth is M must be greater or equal to 2 to the RB upon B. And for our specific example, our RB is 15 and B is 12. So if we look at the value of 2 raised to the 2 times 15 divided by 12, we will find that M must be greater or equal to 5.66. But with the modulation schemes that we've looked at, the number of waveforms that we use, which is capital M, is essentially a number which is a power of 2, which means M can take values of 2, 4, 8, 16, etc., etc. So in this particular case, if we are to actually ensure that we meet the bandwidth requirements, we have to choose a value of M which is greater than 5.66 and is given by 2 to some raised to some integer. And in this case, actually, the nearest value of M that we can use is M is equal to 8, which means we would be using 8 PSK because we've been told that it is actually PSK. And with 8 PSK, the actual bandwidth that we would be using would essentially be 2 times 15, which is that 2 RB, divided by log to the base 2 of 8, which is divided by 3, which essentially we will be using a bandwidth of actually 10 megahertz, but we have an available bandwidth of 12 megahertz, so essentially we would be okay. If we had chosen an M of 4, then we would exceed the available bandwidth, because we would then have a required bandwidth of 2 times 15 divided by 2, which is 15 megahertz. Right? So essentially the problem in this case was actually just simply to understand the relationship between the bit duration, symbol duration, and bandwidth. Then the last bit then says, give this constellation diagram, or we at times call it the signal space diagram, and the corresponding waveform. So this is 8 PSK, and if it's PSK, essentially all the waveforms have got the same amplitude, they only differ in phase. And because there are 8 of them, and if we ensure that the phase between successive signals is constant, that phase would be equal to 2 pi divided by 8. So essentially, your waveforms SI would be written by as A cos of 2 pi FCT plus a phase term, which will be 2 pi I divided by 8. The symbol energy for each of the signals is essentially 1/2 A squared TS, which is equal to energy per symbol, because they are all the same. The A, if we need to write A as a function of the energy, we can then just rearrange this equation here and take the 2 onto the other side, take the TS onto the other side, and then take the square root. Then it means that the amplitude A must actually be given by root of 2 ES upon TS times cos. The basis function would be cos and sine, and they need to have unit energy, which means essentially the amplitude of each of the basis functions would be a root of 2 upon TS. So the constellation, then we actually have a psi1, which is the first basis function, and you got psi2, which is the second basis function. and then each of the signals will have actually, with respect to psi1 and psi2, will have an amplitude of root of ES. So essentially this here would actually be root of ES. Likewise, this here is root of ES, and this here is root of ES, etc., etc. Because the distance from the origin to any of the points is essentially given by the square root of the energy of that signal. In this case, they all have the same energy, so it will be root of ES. Essentially, actually, we can also write our waveforms SI okay, in terms essentially of the root of ES, and then in terms of psi1 and psi2. Okay, so that's that. Are there any questions on that one? All straightforward? Okay, can you hear me?
Yes, we can.
Oh, good. Okay, that's good. Okay, if there are no questions, then let's go on to the next one. Now, this next question says you have 8 quadrature amplitude modulation, which uses the constellation below to transmit data at some rate of RB bits per second over an AWGN channel, which has a single-sided noise power spectral density of 0.8. So essentially, the signal constellation tells us, because it is QAM, we immediately know that we can actually write our constellations, our basis function, and say this one here is equal to root of 2 divided by TS, where TS is the symbol duration, then cos, that's a cos there, cos of 2 pi FCT, that will be that one. And this one here would also be the same. It would have a root of 2 upon TS and it will then have a sign. And this would essentially be 2 pi FCT again. So essentially, those are our 2 basis functions. Now, it means then, yes?
So isn't the basis functions what they're given us below, or is that part of another?
Oh, sorry, yes. Right, so I hadn't read the rest of the question. So in this case, actually, the basis functions are already given. Okay. So psi1
Sorry.
is...
So just going back to the basis functions that you were writing out. So I remember we had a brief discussion last week about the E0 and then the ACM and the AQM that's given in the notes.
Right.
I just wanted to clarify, like, for like test and exam purposes, can we just assume that it would always be spaced with a minimum distance of 2?
Well, okay, it depends on the modulation scheme. It's possible to have a modulation scheme where the distance is not the same. In this case, you are specifically actually given the distances. So you are given the coordinate of this point here is 2, 2j, and this here is 6, 2j, etc., etc. If you could have been given some strange looking constellation where one point was here, and then another point was there, and then another point was here, another point was there, etc., etc. Right? And so in this case, one would be here, another one would be here, and then another one will be here. It's quite possible in this constellation that the distance between this and that would be different from the one between this and that. It could be different between this and that. It's quite possible to have a constellation like that. However, generally, with most modulation schemes, what you actually try and do is to ensure that the neighbors are of a particular point have got the same minimum distance. That generally they will have the same minimum distance, which means if we compare, we take this first point here, the distance from there to there will be equal to the distance from there to there, and it will be the same as the distance from there to there. Generally, you do that. So that, for instance, in this example here, you would also then try and make sure that this distance is the same as that distance and is the same as that distance. But it's not a necessity. It's not necessary. Once you actually have determined essentially the basis points, it simply means the distances simply come from whatever the basis point is. Essentially, it means you have determined your waveforms S1 to S8. In this case, you've got 8 waveforms. And for each of those waveforms, you resolve them into your signal space, and the coordinates simply come from whatever that resolution is. It might turn out that the distance between adjacent points are the same or that they are different. Although in practice, we tend to actually design our constellation such that the distance between successive points are the same. Okay, so in this case then, the basis function are psi1 and psi2, and to confirm that these are unit energy, if we integrate the square of psi1, we would find that we would have 1 upon root 2 all squared, which is 1/2, times 2 gives us 1. Similarly, with this one, if we square this, we'll end up with 1 upon 2 times 2, which gives us 1. Sorry, was there someone going to ask something?
I had a follow-up question, but I can ask after.
Oh, okay, okay. Right, so the first part here is determine the data rate. Now, in this case, if we look at it, ideally, this actually should simply say determine the maximum data rate. Okay? If we look at psi1 and psi2, they go as far as 2, which means ideally, if you're going to have the maximum data rate, then you need actually one waveform to be transmitted over 2, and then the next waveform to be transmitted over 2 seconds, and then the next waveform over 2 seconds, etc., etc. So this could be essentially one waveform Si, or let's say S7, and then the next one could be, let's say, S3, then the next one could be, for instance, another S3, and then the next one could be an S1, etc., etc. Okay? Now, it means then that the symbol duration then in that case would be equal to 2. Therefore, the symbol rate is going to be 1 upon 2. But each symbol carries log to the base 2 of m bits. So the symbol rate is 1 upon ts, which is essentially 1 upon 2. But then each symbol carries log to the base 2 of m bits. Then the base bit rate then becomes the number of bits per symbol, which is log to the base 2 of 8, multiplied by the symbol rate, which is essentially 1 upon 2. So essentially your net data rate in this case would essentially be 3 upon 2 bits per second. The second part then says, determine the average transmit power. for the average transmit power, if we look at our constellation, we find that there is symmetry in the sense that the energy of these two signals is the same as the energy of these two signals, and it's also the same as the energy of these two signals, and is the same as the energy of these two signals. So if we wanted to find the average energy and then correspondingly the average transmit power, if we want to find the average energy, we can find the energy of each of these 8 signals. Add all 8 energies together and then divide by 8. But because of the symmetry that we have, we can essentially reduce the computation by simply finding the energy of S1 and the energy of S2, add the 2 together and divide by 2. Instead of adding all 8 and dividing by 8, we can simply find the energy of the signals in one quadrant and then divide by 2. In this case, because there are 2 signals in a quadrant. So the energy of S1 is simply given by this here is root E1 and this here is root E2. So if we can find E1 and E2, then we can find the average energy of the 2 signals, and to convert to power, we essentially then say energy divided by time gives us power. So root E1 is clearly, the coordinates are 2 and 2, so essentially root E1 would be root of 2 squared plus 2 squared, which essentially gives us 2, root 2. Likewise with E2, the coordinates of E2 are essentially 6 and 2. So root E2 is 6 squared plus 2 squared, the square root of that sum, which becomes essentially root of 40. Then the total energy then is the energy of 1 plus the energy of 2 divided by 2 to get the average energy. And then the energy of 1 is essentially going to be this squared, which is 8. And the energy of E2 is root 40 squared, which is 40. And then this 2 here is essentially this 2 here that we actually have here. And then the TS that we actually have, which is the symbol duration, is essentially 2. So essentially we would have an average transmit power of 48 divided by 4, which is actually 12 watts. So that is the average power that that constellation would actually entail. Then the last part is, if we would transmit S1, obtain a bound to the probability that it will be received in error, which is the symbol error rate. So in this case, we transmit S1. A simple approximation is that S1 is likely to be mistaken for the signals that are closest to it. And in this case, the signals that are closest to S1 are S2, S4, and S5. Now, the probability that you mistake S1 for S2 is simply given by 1/2 error complementary function root of d squared upon 4n naught, where d is the distance between S1 and S2. And likewise, the probability of mistaking S1 for S4 would be given by the same expression. The d is the same in this case as the d for S1 to S2, and the same with actually S5. So essentially, if we calculate the probability of mistaking S1 for S2, then multiply it by 3, the 3 taking into account that we could mistake it for S2, or we could mistake it for S4, or we could actually mistake it for S5. We would then, in this case, then say the probability of error then would essentially be 3, because we have 3 adjacent signals, 3 multiplied by 1/2 error complementary function d squared upon 4n naught, where d is actually the distance between the 2 points. Now, in this case, d can be worked out directly from the constellation. The distance between S1 and S2 is 4, because this here has got coordinates of 2, 2, and this has coordinates of 6, 2, which means essentially the difference is just simply the x-axis displacement, which would be 4. Likewise, the distance between S1 and S4 is 4, and the distance between S1 and S5 is 4. So essentially, we then have 3 multiplied by 1/2 error complementary function root of 4 squared divided by 4n naught, and that gives us essentially the 4 squared is the 16, and this 4 here is this 4 here, and the 8n naught is actually given. And because we want to use tables instead of error complementary function, we use essentially the error function, but then we'll have to say error complementary is 1 minus error function. So this then essentially, if we look at what is in the square root bracket, it reduces to 2.24 if my arithmetic is correct. And then we simply look up 2.24 on the error function tables. And if we go back to our error function tables, so we want 2.24. Okay, so 2.24 is halfway between 2 and 2.5. So it is somewhere within here. And this is 0.995, and this is 0.995. A rough approximation says, well, I can make that about 0.999. So it is 0.005 above and 0.005 below. So that's actually a reasonable value to put in the middle. So then it means that we're saying that error complementary error function of 2.224 is about 0.999. Then the error complementary is 1 minus 0.999, but we also have a factor of 3/2 that we need to take into account, and that gives us approximately 1.5 times 10 to the minus 3. So that would be essentially the error rate. You have on average 15 errors in every 10,000 transmitted symbols. These are not bits, but these are symbols, right? Because we're looking at the symbol error rate, the probability of mistaking a particular symbol. Okay, any questions on that one?
I have a question.
Yes.
So the power of this question seems to differ in calculation to the one in question.
The power differs from the one in
Question 5.
question 5.
It seems in question 5 we don't divide by half to find the average energy.
Oh, okay. We don't divide by half.
Yeah, as we do in this current question.
Oh, okay. But we divide by 8. So in question 5, we found the energy of this, and then the energy of that, and then the energy of that. We added all 8 energies and then divided by 8.
Okay.
I could actually have said that from symmetry, okay, that these two are the same as these two, are the same as these two, are the same as these two from an energy point of view. And then I could simply have taken the energy of this plus the energy of this and divided by 2. I would have got the same answer. Because then instead of actually having this 4 here and this 4 here, I wouldn't have those 4s because I would simply be considering 2 signals. And then I would divide by 2 here, and then I'll end up with the same answer.
Oh, okay. Thank you.
Makes
Sorry
sense?
about that.
Okay. Okay. Any further questions?
Sorry, I had a few questions, but like just from kind of other questions from the tutorial, and then also just to clarify on one of the points that you made for this specific question.
Okay, so let's deal with the questions on this one, and then we can go to the others.
Sure. When you were discussing the red diagram that you've kind of drawn, would that still be considered a QAM system?
Yeah, the QAM is actually a general case. Okay, essentially, when you actually have a 2-dimensional system, you can actually call it QAM. Although in a practical modulation scheme, a QAM uses basis functions that are sine and cos. So if you are not given a basis function at all, and you are told that this is 8 QAM, then you would automatically assume that the basis function are sine and cos. But if the basis functions are specified, then in that case, then you will have to actually say you use those basis functions. Typically, in communication system, what you find is that the basis functions would be sine and cos, but they might also be filtered, a filtered sine and a filtered cos. So if you look at, for instance, the basis functions that we use in GSM, if you had a 2G cell phone, essentially we actually call them, it's a Gaussian filtered sine and a cos, meaning that it's a sine and a cos, but the shape of the sine and the cos is such that you don't actually have a pulse, getting a cursor, you don't have a pulse which, right, pen, okay, you don't have a pulse which starts at this point and ends at this point, and it's sinusoidal in between. So it's not a pulse that does this. Essentially, what you have is a pulse that does this, but it's also slightly rounded in amplitude. It's like the amplitude is sort of modulated so that you don't have an instantaneous change from one signal to another one. They are all rounded up like that, okay? So it would still be a sine and a cos, but rounded. So generally, when you have an 8 QAM or a QAM system in a practical modulation system, you use sine and cos, although in some cases the sine and cos might be essentially rounded up, might be filtered such that they are rounded off at the edges. Is that answering your question?
I'm still just slightly confused because so I was following where you were saying that it's generally sine and cos, which would then give you like quite a rectangular shape. But then if you specify any other basis function, how is that still a QAM system? Like when we say QAM, like what are we actually specifying then?
Okay, right. So when we say QAM, what we essentially saying is that when you actually look at this, your signal constellation, with respect to the basis function, you actually have signal points that are amplitude variation of each of the basis functions, and there is also a phase term. So if we look at, let's say, let's take these three signals. These four. Let's take these four. These four signals differ only in amplitude. Well, no, let's take two actually. Let's take these two. These two essentially only differ by virtue of the fact that this has got a positive amplitude and this has got a negative amplitude. But if we now compare these two and these two, they now have a difference in phase as well, in the sense that if you look at the phase of this and the phase of this, it's actually different. Okay, so essentially what you actually have is you have amplitude modulation, but in quadrature. You have amplitude modulation in one basis function, and you have amplitude modulation in that basis function. Okay, so the difference between these 2 points are that they are amplitude modulation in this basis function, but they are not amplitude modulated in the psi2 basis function. They have the same amplitude. But if I compare these two, S1 and S4, they have the same amplitude with respect to psi1 with respect to one basis function, but they have a different amplitude with respect to psi2. So it's amplitude modulation, but for a quadrature system. So it means that you got amplitude modulation in the x direction and you got amplitude modulation in the y direction. That essentially is what the QAM means. It's quadrature amplitude modulation. Answering the question, regardless of what the basis function is, because essentially you have an x and a y. That essentially defines that it's a quadrature system. And you have amplitude modulation in a quadrature system. So you have amplitude modulation. There are some signal points that differ because of a different amplitude in the x direction, and some differ because of a different amplitude in the y direction.
Okay, I think,
right?
Yeah, I think I get it.
Yeah, in fact, QAM is actually really a general way of actually representing signals that are in 2 dimensions. Let's consider the case that we looked at earlier, which is essentially the PSK. In the PSK, our signals all lie on a unit circle. So you might have one here, you might have another one here, you might have another one here, etc., etc. Okay? Now, essentially, the PSK system is also a QAM system, but it's a special case of a QAM system where the phase between successive signal points is constant. In this case, however you define the successive signal points, you'll find that the phase terms would actually be different, in the sense that the phase between this here and this here is this angle. The difference, the phase between S5 and S6 is essentially this angle, and this angle is different from that angle. So that is where it differs from the case of PSK. Similarly, if you actually also have FSK, where you are able to resolve your FSK system into essentially 2 basis functions only, then in that case, it also becomes a quadrature amplitude modulation. Even though the differences are in frequencies, because what really matters, and this is a critical point with, and this is why we did all this confusing stuff of basis function. The point is actually, in the end, it doesn't depend on the specific waveform that you use. The specific waveform is related to the basis function. It doesn't depend on the specific waveform. The performance of your system really depends on the projection of your waveforms onto the basis function. So this could have been cos. Psi1 could have been a cos. Psi2 could have been sine. But if the coordinates of that, once resolved into a basis function, if the coordinates of your signals happened to be the same as the coordinate system that we have here, then the performance would actually be exactly the same. The issue of the type of waveform is an implementation complexity issue, in the sense that you would say, well, is it more complex to generate this type of psi compared to generating a psi that actually has cos? Obviously, it's easier to generate a psi that is based on cos, because in electrical engineering, we happen to use oscillators, and oscillators are easy to actually implement. You can get them easily. So it's easy to generate signals that are sinusoidal and cos than it is to generate signals that actually do this. You'd actually have to do some switching of some sort. So whether you use cos or sine or what particular basis function is really a complexity issue that is related to an implementation. It's not related to the communication principle. The communication principle simply depends on the mapping of the signals that you choose onto your basis coordinate system.
Hi, sorry.
Go ahead.
Just before Tali continues with her questions, I just want to ask with regards to the basis functions, are these two orthogonal? Because
yes, they are. Right, yes, they are. Let's take this psi 1 and we take this psi 2, okay? And we multiply them. Between 0 and 1, we will have 1 upon root 2 times 1 upon root 2, which gives us 1/2. And between 1 and 2, we would have 1 upon root 2 times minus 1 upon root 2, which gives us minus 1/2. So essentially, the product of that is essentially a waveform that is 1/2 for 1 second and then minus 1/2 for another second. And essentially, if we integrate that, we would essentially integrating from 0 to 2, this portion here, the area under this portion here would cancel with the area underneath this portion because one is the negative of the other. So they are orthogonal.
Okay, right. Of course. Thanks.
Okay. Any further questions?
Sorry, so I just had a few more questions.
Okay.
Last week we were also discussing, like, if you have two different pulses, and then you switch it on and off, and ultimately I just wanted to clarify that even if it's like the inverse of the pulse, so it's not the actual pulse itself, but the distance between the pulse, that would be considered the minimum bandwidth.
Yes.
Okay,
That's
awesome.
correct. So if, for instance, we were to look at if your pulses had a minimum distance of 2, then in that case, then the bandwidth actually depends on 2 because you are switching your waveform at a rate of every 2 seconds. Now, in this case here, we are switching from S1 to S2 every 2 seconds. But if we were to look at the bandwidth of S1 and the bandwidth of S2, well, let's look at the bandwidth of psi 1 and the bandwidth of psi 2. Psi 2 would require twice as much bandwidth as psi 1, correct? Because essentially psi 1 is a pulse going from 0 to 2. But psi 2 has got a pulse going from 0 to 1. Okay. The 1 to 2 is simply the inverse of the other one, so it will have the same pulse shape. So essentially, the bandwidth dictated by this is twice the bandwidth dictated by that. Okay. So let's say the bandwidth of this, let's just give a number. Let's say the bandwidth of that is, let's say, 1, and the bandwidth of this one, let's just say it's actually 0.5. It means at some times you are transmitting a signal with a bandwidth of 1, and at times you are transmitting a signal with a bandwidth of 1/2. So essentially the net bandwidth that you need would actually be 1, because in fact, when your signal needs a bandwidth of 1, then you have to provide a bandwidth of 1. when it requires a bandwidth of 0.5, you have to provide a bandwidth of at least 0.5. So the bandwidth is actually determined by the signal that requires the largest bandwidth, which is the signal that actually has the smallest switching time. So it would essentially be defined by psi2. Making sense?
But then in the gap between the two signals, like is that more just like a different, like just from an understanding perspective, is that considered the minimum bandwidth just because it's needed to distinguish between the two signals?
Well, that is if it was such that you have a difference between the two signals. In this case, you don't. Because if you have, let's say, a 1 and you have a 0 and you have a 1, and the difference between this is essentially the difference between those is 2. Let's just simply compare, let's just look at the psi1 and psi2. Okay, the S values are essentially psi1 and psi2 multiplied by some constant values. Okay, so psi1 is S1 is 2 times psi1 plus 2 times psi2. Okay, so essentially the bandwidth is really determined by the psi1 and the psi2. So essentially within here, if you were transmitting a signal that only depends on psi1, that signal actually would start at this point and it would actually continue and stop at this point. And then the one for psi2 would start at this point. Well, let's put it positive. It started at this point, go negative at this point, and then go positive at this point. So the minimum time between switching essentially from some positive value or from some amplitude value to a different amplitude value would actually be 1 second. But bear in mind that actually the waveforms that you have, like S2 is actually 6 times psi1 plus 2 times psi2. Okay, but the change in the amplitude in time would be essentially determined by the psi2, which essentially has the minimum switching time. So essentially the bandwidth is determined by, in this particular example, by this time here.
Okay, I think I understand. And then
Okay.
just in terms of if they weren't both pulses, is there any shortcuts to figuring out the bandwidth than just taking the Fourier transform?
Well, it's essentially the bandwidth is related to the Fourier transform. Okay, so if for instance this here was actually some waveform that did this, right? Then essentially the bandwidth is simply dependent on the Fourier transform of this ramp function. Okay. But what you will find is that the bandwidth actually, if you're defining your bandwidth as the bandwidth from the first 0 before the main peak to the first 0 after the main peak, then it actually depends on these two. It depends essentially on the point where you actually have an abrupt change, which is essentially in this case these two, because essentially whatever the power spectral density of this will be in frequency, let me do this and get a bit of space. Can you still see my slides on my screen? So,
Yes.
right. If we have a pulse, let's look at 2 of them, 3 of them. If you have something that does this and then it has an abrupt change here, and if I compare it with another one which actually would be this constant and then it abrupt change here, and let's call this essentially 1 and we call this essentially 1, and then let's take another one where in this other one, I will do this, and then an abrupt change here where this is 1. Because this here is 1, and this here is 1, and this here is 1, your bandwidth is actually going to be determined by that, by this one. So in the frequency domain, what you might actually find is that this here, you know that it gives you a sine x upon x, which means it will give you something that does this, and does that, and does that, etc., etc. What you find is, if you were to do the Fourier transform of that, it would still give you a 0 at this point, and it will give you a 0 at this point, but the shape here and the shape there could be different. So it might give you something that might actually do that, go to 0, and then it might do this and go to 0, etc., etc. As long as you are essentially terminating the waveform at 1 and switching on to a different waveform, then what you will actually find is that your power spectral density will always have a 0 at this point here, which is actually going to be at 1 upon Ts, where Ts in this case is 1. Okay? The shape here would be different. So if you wanted to find the exact shape, you would have to do the Fourier transform of this to get this shape here. Or if you wanted the shape that you get for this one, you'd have to do the Fourier transform of this. But whatever is Fourier transform, it will always have a 0 at this point, and it will have a 0 at this point. In fact, I mentioned earlier that in an actual transmission system, we tend to prefer rounded shapes. So what you find is we actually, instead of this, we would prefer to use a shape where we transmit something that actually is rounded at the edge. The net effect of that is you will have a power spectral density which will still go to 0 at this point, but because it's rounded, what you'll find is you get a power spectral density, different color pen, power spectral density, which would do typically this. And then here it will have a very small side lobe. So essentially by doing that rounding up, oops, that's too much. By doing that rounding up, you actually push a lot of the energy into the main lobe. And then your side lobes essentially are much smaller than the side lobes that you get from a rectangular function. But nonetheless, what you find is it will always go to 0 at this point. So the bandwidth requirements would actually be the same. Okay?
Okay, thank you. That makes
Mm-hmm.
sense. Question just from the last test, more just to do with the representation of triangular functions. I remember emailing you, and I just wanted to get confirmation for the 2 different ways in which a triangular function can be given the expression.
Right, yes, it's a matter of notation, because
okay,
you're talking about the rectangular function.
No, so the triangular function. So
the triangular function, right?
And the textbook that we're currently using has a different formula for what is being given in LATI.
Okay. What I would suggest is use whatever formulation is in the data sheet that I gave you.
So I don't think that the triangular function is defined in the data sheet.
Oh, is it not?
No. So the difference is the bandwidth. For the one representation, the bandwidth is double the other, as in the notation.
Okay, triangular function. Okay, I'll email the class and actually give them the one that you should use. And unfortunately, I can't. I've already submitted the exam paper, so I can't recall the exam paper and actually change the data sheet, because the data sheet is on the exam paper. But maybe what I'll do is I will send you, because the exam is you do it at home. So I will also send you the Fourier transform of the triangular function that you should use, so that you can have that on the side if it's not on the data sheet, as you say.
Okay, thank you so much.
Right. Okay, guys, I have to go now.
Sorry.
For the exam, guys, what
Sorry.
I suggest is go through the tutorials and make sure you understand the tutorials. And remember, don't learn a formula approach, because the problem could come out, it might be essentially the same problem but phrased differently. So try and actually understand why we're solving the problem in that particular way, so that if the problem is posed differently, which it will be in an exam, it won't be the same as in the tutorial, but the concepts are still the same concepts, which means if you understand the concepts in the problems in the tutorials, you should be okay with problems in the exam. And the problems in the exam, they are, in a usual exam, I ask you to answer 4 questions. But in this time round, you'll be required to answer only questions. And then you even have a lot more time. You've actually got 4 hours. The comment that came from the external examiner was actually that the paper is essentially too short compared to the 4 hours that have actually been allocated. So essentially, you've got 4 hours to do what is typically a 3-hour exam. If anything, it's actually even less than a 3-hour exam, because it's 3 questions instead of the usual 4 questions. But at the same time, you will actually be expected really to think about the questions. So it's not going to be the same as where you actually flip back to the tutorial, see how it was solved in the tutorial, and try and follow it. It will not be the same. It's going to be worded in such a manner that it is actually an exam which is done open book and open Google exam. But you should be okay. Last question.
Sorry, sir. The test tomorrow. Should we just focus on the tutorials and do those properly?
Okay, right. The test tomorrow, and I'm actually going to send an email to the class later on. The test is only on the digital modulation stuff. Right? So similar to this tutorial that we were doing, it does not cover any of the FM, does not cover any of the amplitude modulation stuff. It's only on the digital stuff. The digital stuff, what did we do? We essentially did 3 things. We did the first one, which was actually looking at how, given any 2 signals, you can convert them to basis functions and hence get the bit error rate. Then we looked at practical modulation schemes, which were ASK, PSK, and FSK. And then lastly, we looked at the multi-level modulation. And multi-level modulation, essentially, it's similar to the last 2 questions that we did in this tutorial. So the test only covers those elements. It's actually 1 question which has got 4 subparts. The 4 subparts essentially cover the range, the whole range that we've talked about: basis functions, BPSK modulation, multi-level modulation. Does that answer your question?
Yes, sir. Thank you.
But I will send this afternoon an email to the class, essentially with the same sort of instructions and same sort of information.
Yes, sir.
Well, okay. All the best with the test and the exam. The exam is really towards the end of the examination session. Please don't leave the reading right to the end. Depending on how many exam papers you have to write, then just simply make sure that you actually do a study time plan to say between this time and that time I'm studying for subject A, and then for that it will be subject C, and then I'll go back to subject B, and then subject D, and then I might go back a little bit and do subject A again, so that you essentially have a schedule. That way you don't inadvertently give less time to some courses and more to other courses. Good luck, and we'll see you next year. And let's hope next year we are going to be back on campus. Although, when one looks at what's happening with COVID in Europe and the US, where they are having a second phase, it's difficult to determine whether we are really going to be back on campus or not at the beginning of the year. Unfortunately, next year, I think you know that the university is starting, I think, a little late. Because the matric students are writing a little late, so the results for matric is not going to be available early. So I think the whole university calendar is going to be shifted to start, instead of starting in February as we used to, it might be a little later than that. We'll see you next year, all of you in 4th year. Good luck. Okay, cheers, bye. If anyone has any question, please contact me. You've got my cell phone number and you got my email number. Contact me if you need any discussion.
Yes, sir.
Okay, cheers. Bye.
Thanks, sir.
Bye.